Hello everybody, this is Mr. Longo here, and in this video we are going to do some more solving with radical equations and equations with funky exponents and stuff. So let's just hop to it and start with the first example, which is the square root of x minus the square root of 6 separately, and then the square root of x minus 6 all underneath one radical. So we have to remember, to get rid of a square root, we need to do the inverse operation, which is squaring both sides. However, squaring the right side is much easier than squaring the left side, because when we square a square root, it just takes the square root away. So the right side is now x minus 6 and the radical is gone. However, remember when we square a set of parentheses, it's like you're going to multiply a binomial times itself. So we're now at the square root of 6 minus, or the square root of x minus the square root of 6 times itself. So when you multiply this, the square root of x times the square root of x is x. And then the square root of x minus the square root of 6 is minus the square root of 6x. And then we have to distribute the negative square root of 6 times the square root of x, which is again the negative or minus the square root of 6x. And then a negative square root of 6 times a negative square root of 6 is a positive 6, because the square roots just cancel each other out. And then we simplify that. We have x minus 2 square roots of 6x plus 6 is equal to x minus 6. Okay, so again, like I said, the right side is much easier to square than the left. But now we could move some stuff over to the other side to get the radical by itself again, because we have to get the radical by itself to square to get rid of that one as well. So now we're going to subtract the 6 from both sides, and we're going to subtract our x from both sides, and that's going to give us a negative 2 square root of 6x is equal to a negative 12. Divide both sides by a negative 2, that's going to give us the square root of 6x is equal to a positive 6. And now we can square both sides again. And that will give us 6x is equal to 36, which means x is equal to 6. Okay? And if you have to write it in set notation, of course, that is a solution, so we would just have 6 is a solution. So that's the first one. Second example. Remember, when you're working with exponents, it's really nice to have the same base, because if they have the same base, you can just set the exponents equal to one another. Now, 3 is already the smallest base we're going to be able to work with, but we can change 27 to 3 cubed, and then cube that. So when we raise an exponent to another exponent, we have to remember that's multiplying. So we have 3 to the 2x is equal to 3 to the 9th power. And since the bases are the same, we can just set the exponents equal to one another. And we have x is equal to 9 halves. Or again, if we're asked to write in set notation, we have 9 halves, because if we substitute it back in, it will leave us with a true statement, and we are good to go. Okay? So that's the first two examples. We have 2 more. Now, of course, at any time, if you feel that you know how to work with either of these last two, simply pause the video and give them a shot and see if you can handle them. If you're not sure what to do, let's go. Remember, a negative exponent just means reciprocal. So this is 1 over 1331, but this is 11 raised to the negative x. So we can rewrite this as 1 over 11 to the x, and that's equal to 1 over 1331. So since our denominators are the same, or since our numerators are the same and our denominators, we just have to set those equal if these fractions are going to be equal. So we can just set 11 to the x power equal to 1331, where really all you're doing is asking yourself, 11 raised to what power is 1331? So 11 to the x is actually equal to 11 to the 3rd power, so x is just equal to 3. Okay? And finally, the last equation here, we're going to have to get rid of a 5th root. But there's a couple of different ways we can look at this. So we have a base of 16, which we could write as 2 to the 4th power. And of course, the fifth root of 4 could be written as the fifth root of 2 squared. So this can actually be 2 to the 4th times 2 to the 2/5 power. And now that's equal to 2 to the x minus 3. Now since we have the same base, whenever you're multiplying, you add the exponents. So 4 would actually be 20/5 plus 2/5 would be 2 to the 22/5 is equal to 2 to the x minus 3. Again, we have the same base, so now we can just take 22/5 and set that equal to x minus 3. If we add 3 to both sides, x is going to be equal to 37/5. Again, if asked for in set notation, we have 37/5. All right. So that's it. Just a few additional practice problems with some examples that are a little bit trickier. Otherwise, that's it. This is Longo, and I'm out. See you. Bye.